So I'm driving to the Keys this weekend to go kayaking with some friends, and I'm in a predicament. Do I drive the kayak I have from Fort Lauderdale to Islamorada, or do I rent one when I get down there? It all comes down to cost. Which is more cost effective? So I'm going to turn to SOLIDWORKS Flow simulation to help me figure this out for sure. To start any flow simulation, I'll need to start a new project, and I always use the wizard. This helps guide me through the process. I'll give my project a name, choose my units. For this, I'll choose miles per hour. Here I decide whether or not it's an internal or external analysis. So for this wind tunnel test, I'll choose external, like the car on the road. The fluid flowing around it's going to be air, so I'll pick that from the list. And this is where I define the speed. Now this box that's around my model is known as the computational domain. That's where flow simulation is going to solve this problem. So I need this rectangle to represent my wind tunnel. I'll just drag the handles, resizing it until I'm surrounding my road and car. That looks good right there. And next, I need to define a few boundary conditions. Now normally, the car is moving and the road and the air around it are stationary. But in this case, we have a stationary car and the air and the road need to move around it. So here's where I will define the boundary condition of a real wall, saying that the road surface is going 80 miles per hour, the exact same speed I defined in the setup. I'll also need to apply a boundary condition to the four wheels. This will be a real wall, and I'll define the rotating speed as the equivalent of 80 miles per hour. And I'll make sure the direction's correct. I'll use the right hand rule to make sure that the vector for the direction is pointing the correct way. And lastly, I'll define a goal. For this, I'm going to use the force acting against the car, the drag force. So this is force X. Additionally, I'll define a second goal. This will be an equation goal, which will give us the drag coefficient. This value is what we use to say how aerodynamic a car is. It's what I'll use to compare my results and make my decision. And with that, we're ready to run our study. Now that I have this one study done, it's very easy for me to copy this onto different configurations so I can run it in batch mode. So I'll clone this. And with that, I'm ready to run the study. And as it runs, you'll see that I can actually preview the results, getting an idea of what's going on before it's actually done solving. So let's take a look at our results. There's a lot of different ways that we can visualize how the flow goes around the car. We can do cut plots, iso surfaces, surface plots. My favorite is flow trajectories, giving me a nice visualization of what's really going on. And after I'm done taking a look at the results, I'm going to look at the hard data, the values for the drag force and the drag coefficient to make my decision. So after looking at the results from flow simulation, it looks like it really doesn't make that much of a difference whether or not the kayak's on the roof of my car. So for this weekend, it looks like I'll be driving my kayak down to Islamorada. And thanks to flow simulation, it looks like that's the most cost-effective way. The increased cost in driving my kayak down will be offset by the savings in not having to rent a kayak. Just like all the other decisions we have to make as engineers and designers, we can look to tools like flow simulation to help us make the best, most cost-effective decision.